Hello guys, today I wanted to talk about Git. Don't worry, I'm not going to bore you with the usual stuff like git push, git pull, merge or rebase. Instead, we are going to talk about something very interesting. These are two different concepts. One, what happens inside your .git folder when you add or commit a file. Second, how does Git actually manage to give you the entire source code back when you switch to a branch, tag or any other reference. Alright, so let's get started. Alright, so before diving into further details, what we'll do is we'll create a simple Git repository in my machine, and then we'll go and introspect the .git folder and see what files are available to us. So you can follow me along. I've divided my terminal into two sections. On left, we will create the Git repository, and on the right hand side, we'll try to go inside the .git folder and see what files are available to us. So we create a directory, we cd into the Git directory, and let's git init. So as it says, it has created a Git repository inside this location. Let's go into that location and do a simple ls-al. So here you can see we have several files which are available out of box to us. Instead of this, let's simply do a tree of the current directory, and here you can see what really is available to us. So inside the default .git directory, we have couple of files which are available to us by default. So as we can see, inside this .git folder, we have 9 directories and 17 files. Alright, so first of these files is called the head file, and head file usually is a commit ID or reference to a branch or reference to a check or a tag. Alright, so let's see what we really mean by that. So if we do a cat on the head file, we get refs head main. Right, let's do one thing. Let's create a branch git checkout minus b, a branch called a. So it says we have switched to a new branch a. Let's verify if we have branches. No, not before we commit something. But at this point in time, if we cat on the head again, we will see this branch, this cat now points to a. Let's switch back to git checkout main, and here we can see the head again points to the main. Alright, so far so good. So next file in our directory is the config file. Let's see what's inside that. And here you can see the config file basically holds information about the current repository, right? Right now this repository is not connected to any remote like GitHub or GitLab, so it doesn't contain any information, but any such information, who is the committer, who is the author, what is the remote, all these information are contained in our config file. The next file in our directory is the description file, and this description file basically is from one of the legacy applications, and it just says unnamed repository. I did this file description to name the repository. It's not a lot of any relevance to us, so let's continue. The next in the list is the hooks directory. So the hook directory basically holds scripts, various scripts that you can run to hook into the lifecycle of your regular Git operations. For example, this pre-commit script can be configured to do some operations before you commit your changes, and it can be used to do stuff like lint your code base, run unit test or code formatter before the commit. We'll keep this specific directory out of our scope for discussion today. So let me just change this tree structure here. Tree hooks, yeah. So now we have only the relevant directories that we will discuss. Next in our list is the objects directory, and this is the meat of our whole discussion. Let's come back to this later, and let's quickly discuss about what does the ref directory hold. So ref directory basically holds the refs or references to all the branches, tags, heads, when we do stash, pop, etc. All those information are actually held into your refs directory. Now before we discuss the details of the objects directory, let's have a quick preview of how the content of the objects directory change when we add and commit file. So in order to do that, I will quickly run this command. So this command will refresh on every half a second and show us the files that change. Let's see what happens when we add a few files to it. So we'll start by creating a file called a.txt. We'll write some content to it. Right, and then let's add this file. And here you can see under the objects directory we get an object. Alright, let's do and commit, initial commit, and then you can see it created two more different files. Right, let's get down to the details of these and see what these really hold. Alright, so let's try to see what is the content of these files. That Git objects OE 50, and here you can see this is a binary file. Let's also try to check the contents of the other two files that we see, which is D9. This again is a binary file, and finally F9 is again a binary file. Alright, let's also try to understand what is the actual file type of these files. It's a zlib compressed data. I guess it's the same for other two files. Zlib compressed data. And again, zlib compressed data. So, in summary, what happens is whenever we add a file to Git, it creates a zlib compressed file and adds it under the objects directory. Same happens when you do a commit, right? Now, Git provides us with few utility commands in order to inspect the content of these files, right? So let's try to do that. Command is fairly simple. We say git cat file, and then we have to use this hash, which is OE and but in order to get some information, we have two flags. One is -p, which tells you what is the content of the file, right? Similarly, we can do D9 this whole hash, and it tells us, gives us this entry. Similarly, say F9 and rest of this. And this basically shows us that this is some content. Now let's run the same three commands with a different flag. -t tells us the first file is a commit. The second file is a tree, and the third file is a blob. Right? So basically, whenever we do a git add and git commit, Git basically transforms these files into three different type of objects. One is a commit, one is a tree, and one is a blob. And -t flag in git file command tells it what type of file it is. So in short, whenever we do a git add and git commit, it creates three types of objects under the objects folder. First one is a blob, second one is a tree, and third one is a commit. And commit basically includes the details about the commit, the tree which this commit points to, and then if you see exactly this tree, you would see this tree refers to this blob, right? And this blob basically represents the SHA-1 hash of this file called a.txt. Alright, let's make a few more changes. We first start by adding one more file called b.txt. Let's add this file and let's check our tree. Now, what has happened now is it has now added this new file called da2068. Let's see the content of this file. And then it shows us the content of this file. Let's also check the type of this file. And this is of type blob. Let's now try to commit this file. And now you can see it created a new commit. The commit ID is this, ddodda. So let's see. Minus t first. It's a type of commit. Let's check the content of it. It contains a tree, the parent, which was the initial commit, and then some details about author and committer. So let's now inspect this tree. Get cat file -t of this, which is a tree, and then -p of it will tell us what are the content. And here you can see it has two contents, one referring to the file A and another one referring to the file B. Let's quickly just introspect the content of these two hashes. Cat file -p of the first hash. This is some content, which was our a.txt, and get cat of second blob. This is the second file. So what has happened here now? When you add a file to Git, it creates a blob. When you add a commit to a file, what it creates is three different objects. One is the commit. Commit contains information about the blobs and the trees which form that commit. If you introspect the tree, it can actually contains further trees or information about the blobs that contain that tree. So basically every git commit provides you a hierarchy of tree and blobs using which you can navigate and find out which exact files were added into that commit. Alright, so let's summarize what we have learned so far. All the files in the Git repository are stored as blobs, right? The blobs are represented as SHA1 checksum of the file content. Then every time when we add or delete something from the file and then git add the file, the SHA1 checksum changes and a new blob is added to the objects folder. Now coming on to trees, trees basically represent a directory structure. They represent which files were part of which tree structure and provide a hierarchy through which it's possible to identify all the files under the tree. Finally, we have commits. The commits represent the snapshot of the current working tree. It holds some additional information like committer, author, the commit message, and the timestamp. Now let's also look at the example of what happens when we make a commit. When we add a file to a Git, for example a.txt in our case, it created a blob starting with 595C11 in objects folder. Then during git commit, it first creates a tree with SHA starting with 5D9C and the content pointing to the blob 595C11, which is the previous step. Finally, a commit is created starting with OE50D9 that points to the tree starting with FD9C and some additional metadata like author, committer, commit message, and the timestamp. Let's see what happens when we add a file b.txt to the working tree. When we add the file, a new blob with SHA starting with DA2068 is created. Now notice that the blob for a.txt remained unchanged. On commit, first a new tree is created with first blob pointing to a.txt and the next blob pointing to b.txt. Right? Since at this point the content of tree has changed, therefore the corresponding SHA1 checksum of the tree has also changed. Finally, Git creates a new commit object pointing to the new tree with new commit message and the metadata. So we witnessed two different snapshots of the repository represented by two different SHAs. With every commit, Git creates a new tree and blob combination of the files or the objects that have changed. And with every checkout, Git exactly knows how to parse the tree and which blobs were part of which commit hash. However, you should understand that SHA hash for any file that was not changed remains intact, and no new objects of those files are created. Therefore, Git can actually optimize storage by reusing the hashes of the unchanged files. Coming back to the terminal. Now let's check one final scenario. What happens when we make the change to all the existing files? Right? So we have a.txt and b.txt and we'll make changes to both the files. Here we updated a.txt and let's update b.txt. And this will create two new blobs. and we can see on the right hand side that we have 2 additional blobs. Let's commit this file. And now we can see that a new commit is also created. Let's go and inspect what happened on this commit. So now you can see this commit points to this specific tree. Let's inspect that. Which in turn points to 2 new blobs. And if you check the content of this new blocks, this is the new content which we added on file a.txt, and similarly for file b we'll see the same comment. So you can see that this time the commit pointed to new tree with entirely new blobs, since both the files were changed. Hope this helps you to understand how Git represents the snapshots of your commit inside the .git folder. Now before closing the discussion, I want to focus on one final thing. If you check the objects folder, you would see that blobs, trees and commits are not directly stored under the object directory with their specific SHA. The first 2 characters of the SHA are used as subfolder inside the object directory, and rest of the SHA is used to represent the file name. Now this is because in some of the legacy operating system and file system, there is a limit to the length of file names and number of files that can be stored under a directory. And this is Git's way to optimize any such problems with legacy file systems. Hope that explains how Git works internally. Please let me know if there are more details that you would like me to cover. See you.